Okay, so I'm going to start the intro over. Kara Rudolph is joining us from Columbia University, where she's an assistant professor of epidemiology. Her research interests involve developing and applying causal inference methods to understand social and contextual influences on mental health, substance use, and violence in disadvantaged urban areas of the United States. So with that, I'm going to turn it over to Kara, and looking forward to the talk.
Hi, everyone. Thank you so much for having me. Can you see my slides okay? Any thumbs up? Yeah, perfect. Okay. Well, as I said, thank you very much for having me. I'm excited to be here, at least virtually. I also want to mention I have two little kids who are at home, so you might hear them in the background. But my husband is watching them, so have no fear. And like Robbie said, please interrupt with questions or comments so that this can be as interactive as possible. And so today I'm going to talk about some work I've done with collaborators trying to better understand reasons why intervention effects may differ across sites. So in multi-site trials, for example. And so understanding reasons for differences is actually, I think, a really hard problem, and realistically, not an attainable goal to fully understand them. But we have focused on developing what we call transport estimators to account for some of the differences across sites that could then result in the effects differing. Okay, so here's an outline for the talk. So first I'll talk about the study that motivated this work. Then I'll talk about estimating transported total effects, followed by transported direct and indirect effects. These are like the mediation effects. So the study that motivated this originally is the Moving to Opportunity Experiment, or MTO. And some of you may be familiar with this. This was a large-scale randomized control trial that was conducted by HUD in the 1990s and extended into the early 2000s in 5 cities in the United States, which I'm showing here. So families living in high-rise public housing in these cities could sign up to be randomized to receive a Section 8 housing voucher, which is a form of housing assistance in the US that still exists today. People still, people use these. And what they do is families can use the voucher to subsidize their rent. That can allow them to move out of public housing where their rent is subsidized and apply that subsidy to a rental in the private market. The idea with MTO was that this randomized assignment of the voucher would then encourage these families to move out of their high-rise public housing apartments and then into rentals, ideally in lower poverty neighborhoods, though that didn't always happen. So the families were randomized. They were followed for about 10 to 15 years with 2 follow-up surveys. And so we're going to use data. I'll be showing you data from this full length of follow-up time. There's been a ton published on MTO, actually, and in such a vast literature, there are actually many examples of differences in MTO's effects across the sites. And so I'm showing an example here for the effect of voucher randomization on risk of using marijuana later in adolescence. And so just for this one little example, you can see that in Boston, this is an example of what could be considered an unintended harmful effect, where being randomized to the voucher actually increased risk of marijuana use in Boston, but that wasn't the case in the other sites. And there could be multiple reasons why intervention effects could differ across sites. So first, there could be differences in site level variables related to maybe the intervention design, how it was implemented, or contextual variables like the economy that would modify intervention effectiveness. And so such variables suggest that the intervention either isn't the same or it doesn't work the same in the 2 sites. Second, there could be differences in person level variables, or what I'll call compositional variables, and they could also modify intervention effectiveness. And so that could also cause the overall marginal intervention effects to differ across sites if these person level variables modify the effect of the intervention, even if the interventions are structured and implemented in an identical fashion. Also, there could be differences in the mechanisms, producing some intermediate variables along the pathway. And I'll talk about these more later when we talk about the direct and indirect effects. So in many cases, it's not reasonable to assume that the effects, these marginal effects, will be the same in different populations. And these latter two reasons, so number 2 and 3, could cause the intervention effects to differ across sites, even if the interventions are otherwise identical, like they're structured in the same way, implemented in the same way, which is probably pretty close to MTO. So Section 8 vouchers, like I said, are a national form of housing assistance. So the vouchers themselves are the same across the sites. And MTO researchers really went to pretty great pains to have it be implemented as identically as possible across the sites. But when I started working with these data during a postdoc, I was surprised that even though these differences existed, they're pretty much ignored when people actually did the analyses in the literature. And so I'm giving an example here with a quote from the interim impacts evaluation, where they said with only 5 sites, which differ in innumerably potentially relevant ways, it was simply not possible to disentangle the underlying factors that cause impacts to vary across sites. Okay, so what was done for these thousands of MTO papers? So the vast majority of the time, site was and is included as a covariate in whatever regression model was being fit, and that was that. And so what does that do? That usually assumes that we expect the conditional intervention effect in one site is the same as in another site. A tiny, much smaller chunk of the time, folks estimated site-specific effects, which is, I don't know, I think of it as kind of on the other end of the spectrum. So it assumes that effects, even conditional effects, are different across the sites. And the implication there is that we actually can't learn anything about how the intervention will work in a future city based on how it worked in another city. Also, evidence wasn't used, to my knowledge, to inform the decision about 1 versus 2, whether we control for site or whether we estimate these site-specific effects. So this work was really motivated by me being curious, is there a third option where we can look to the data for evidence to inform, okay, how should we handle site? And so Pearl has written pretty extensively on this idea of transportability. And so I wondered if I could use some of his reading to help us understand why these impacts varied across sites. So in the case of MTO, transportability would involve applying the results of an experiment in one site to a different target site, accounting for differences in population composition, take-up, or actually using the voucher between the 2 sites. So for example, in Boston, we saw that getting a voucher increased risk of later marijuana use. And using ideas of transportability, we can then ask, well, what do we expect the predicted effect to be in New York City? And in reality, New York City saw a null effect. So we could ask, if we accounted for these differences in population composition, actually using the voucher, would we have predicted this? In the most basic cross-sectional case, where we have covariates, treatment, outcome, this is not a new question. So post-stratification, direct standardization have been around for many decades. And then we have a whole bunch of model-based approaches that have improved upon these original methods so that we can standardize based on a whole bunch of variables, continuous variables, et cetera. And then Pearl and Birnbaum really formalized the theory and assumptions for transportability in this area. So what we did is we piggybacked off of Pearl and Birnbaum's work, and we extended their transport formula for multi-site encouragement design interventions. And so I'm showing that setup on the right, where A would be randomization to receive a housing voucher. Z would be moving out of public housing with the voucher, and Y is the outcome. So in the example that we've been using, say later marijuana use, W are baseline covariates, and then S is site. So in this setup, A is what's called an instrumental variable. So there's an exclusion restriction in that A doesn't directly cause Y. It's assumed to only affect Y through its effect on Z, which in the case of MTO is reasonable. People usually assume it because they assume that being randomized to receive a voucher or not shouldn't really affect your outcomes unless you actually use the voucher. So also corresponding with Pearl's notation, we use an arrow from S into a variable to denote where a variable's conditional distribution depends on S. So for our MTO example, we assume that site influences the distribution of covariates, the likelihood that a family actually uses the voucher to move Z. But we know that S did not influence randomization, and then we assume that it does not influence the outcome conditional on the other variables, which is the crux of this transportability. And then our other contribution here with total effects was to develop an efficient, robust estimator to estimate various total effects that one could estimate under such a data structure. Okay, so we were interested in three transported total effects. So the first was the intent to treat average treatment effect of the instrument, so of being randomized on the outcome in the new population, so in the new target population. That's this first one. We were also interested in the average effect of the exposure. So this is not actually using the instrument, so there still could be subject to unobserved confounding. So that's just contrasting, of course, the expected outcome of Y under Z1 versus Z0, again, in the target population. And then lastly, this is this complier average effect that's kind of a typical effect that we might estimate with an instrumental variable type analysis. And so that is the effect of Z on Y, again, in the transported population, but among compliers. So that is using, really harnessing this instrumental variable that we have. And so I'm going to focus on this complier average effect because you'll see that the intent to treat average treatment effect is included in it. And so it's kind of nice we can address both of them. Okay, so here I'm showing the identification for this complier average effect from the observed data and then the assumptions that we need to identify it. You can see that it's a ratio of 2 effects. So the intent to treat average treatment effect is in the numerator, and then the average treatment effect, the average effect of A on Z is in the denominator. The first assumption, which I talked about before, that's that assumption where we're assuming that there's no arrow from S into Y. And that's arguably the strongest and likely to be the most problematic. And that's assuming this common outcome model across the sites. So that just means, again, that S is not related to the distribution of Y, conditional on the other variables. So if we are in a situation like MTO where we do happen to have data on Y for the transported site, we can actually test this assumption non-parametrically, which I'm including in this citation number 8 below. And then we also have the typical exchangeability assumption, positivity assumption, and then because we're talking about a complier average effect, we have these 2 other instrumental variable assumptions of exclusion restriction. So here, number 3, and then monotonicity, number 4. And then what we did is developed a targeted minimum loss-based estimator for each parameter. And so this is a type of estimator that's based on what's called, based on solving what's called the efficient influence function. And estimators that are based on the efficient influence function have some nice properties in that they have, they're either doubly, multiply robust, and one can use machine learning in fitting your models for them while still retaining appropriate standard errors and confidence intervals. And then another nice part about the TMLE estimator in particular is that it's a substitution estimator. So it'll stay within the bounds of the parameter space, which we thought might be especially important in this case where what we want to estimate is actually a ratio. So it might have some problems otherwise in terms of estimates going outside the bounds of what's allowed. Okay. Well, and as you may be thinking too, having this ratio of 2 estimators, so we actually, what we did is had like an estimator for this numerator and an estimator for the denominator. We've since improved upon this, but so you might be thinking that having this ratio is problematic because then you could have a lack of compatibility between the models that you're fitting in the numerator and then in the denominator. So we've since improved upon that. But for this, that's how we did it. We made an estimator for the intent to treat average treatment effect, an estimator for the average effect of A on Z. And then for D, I'm showing just very this without detail really, but this is the general structure for the efficient influence function for this ratio, which is given by D, which is just the quotient rule for getting a derivative of a ratio. And then, like I said, there is this problem in that because we have an estimator for the numerator and a separate estimator for the denominator, we can have incompatibility. We fixed this problem in later work, but I'm not going to talk about that here. Okay, so we have an estimator, and so here I'm just giving the robustness properties here. So if you meet either one of these 3 cases, then we would expect the estimator to be consistent. And so you can see too that we're like the different models that we're estimating to actually solve this efficient influence function. So we have our outcome model, our model of how the sites differ, the Z model, which is actually using the voucher, and then A, which in this case is randomized. And so we did simulations to test this out in finite samples. And so this is basically showing what we expect. So it should be consistent when all models are correctly specified. It is. And then here's this one case of misspecifying S and Z, which falls within our robustness property. So it should be, consistent here to yes. And we don't expect it to be consistent when we misspecify S, Z, and Y. And that is what we see. I was also interested, we have practical positivity violations with the MTO data. So I was interested in seeing, okay, well, how well does it perform in a simulation where the data looks like MTO in terms of, not only the sample size, but the presence of these practical positivity violations. And for those who aren't familiar, that's when you can get some small probabilities. And that's a problem because then we don't expect, you can get bias, your variance can blow up, things like that. So we just want to
Kara, can I, this is Jennifer Hill. Can I slow you down a little bit? Just because it's a lot. Like, I'm familiar with most of these issues and I'm still falling behind. So I just want to just to make sure that people in the room may be kind of caught up to what's going on. So first of all, I've been trying to keep track of what all the letters mean. So can I just confirm what all the letters mean? So S is site. Okay. W, is that like covariates, like the demographics in the site?
Yeah, like baseline covariates, exactly.
Baseline covariates, okay. Yep. So mostly we're dealing with that like option 2 from the past, right? Of like the way that things can vary has to do with, in the sense that you've got instrumental variables, there's also a 3 in there as well.
Yeah,
implicitly. Okay.
Yeah,
so what we're dealing with, go on.
So yeah, that's a really good point. Thank you for stopping me. Yeah, so here, in this case, we're really focusing on these 2 arrows. So S pointing into W, S pointing into Z.
Yeah, okay. So those are the ways that, and Z is what you actually did.
Yeah, did you use the voucher?
A is how you were randomized, but Z is like, I actually took the voucher or I didn't.
Exactly.
And then Y could be like an educational outcome or a crime outcome or a health outcome.
Exactly. Yeah.
Okay.
Yeah. And that's a good point too. MTO, oh my gosh, studied so many outcomes, as I'm sure a lot of you know, like education, economics outcomes, health. Yeah.
Okay. So, and I'm seeing there's a question in the chat about the positivity violation too. So in practice, that would really be that you end up with that the difference, like there might be a kind of person who would take up the voucher who you just wouldn't even see on the other side, right? Or vice versa.
Exactly.
The way it could
Exactly.
arise in practice.
Yeah. Yeah. Or maybe you would see like, you know, you might have like only one person in this other group that's like standing in for a whole bunch of people. So either you don't have any support or you have poor
Very
support.
little. Yes.
Yeah.
Okay. All right. I think I'm mostly caught up, but oh, good. Neil's got a question.
So while Jen, I also want two clarifications. So the exclusion restriction that S doesn't affect Y directly, but only through W. So suppose there are unobserved variables. So in Los Angeles, everybody initially was a marijuana user. And, you know, or nobody was using it. So the effect would either be, you know, low or high. So you're basically assuming this is all through W and you can observe all the components. So it's only observables that are going to affect Y and not unobservables. Is that a correct interpretation?
Well, I guess two things. So one is A is randomized.
Well, I wasn't worried about A. I was worried about there's no arrow from S to Y, only through W.
Right.
A is fine. A I'm perfectly happy with.
Yeah. So, I mean, I guess we wouldn't expect. So I guess I was going more in the direction of like, you know, baseline variables we would expect because A is randomized, we would expect them to be roughly balanced. But yeah, so in terms of why in my little example was later marijuana use, so marijuana use in adolescence, as opposed to the kids who I'm looking at here, they were on average like 4 or 5 at randomization. And then, you know, then this is looking at them 10 to 15 years later. So when they're like later adolescents.
Yeah.
So yeah, like this is really, in my mind, really saying, okay, anything that's affecting Y, we're accounting for, like you said, like observable variables, and there's no difference in this in Y conditional on these observed variables between the sites.
Yeah. So suppose Los Angeles schools had a huge anti-marijuana program that nobody, and you don't, and that, again, if you observe it, it's fine. You don't observe, you know, you don't know what's going on in Los Angeles.
Right. Yes. Yeah. Yeah. And if you observe it, and yeah, and that's interesting that I'm going to talk about when we talk about the mediation, school factors, because that is a big, of course, a big deal about what's happening. But yeah.
Thank you. And one other clarification question on the results. We have the mean squared errors. How can you have such huge bias? So it looks like the most biased estimator by a lot has less mean squared error than all models correct. And that's, so I'm a little confused.
Oh.
Such good mean squared error properties.
I agree. That might be a typo.
Okay, fine. Yeah. Always a good answer.
Yeah, I would have, I mean, that does seem weird. I typed this in instead of using what I could have used, which is X table, but so.
I'm gonna unvideo myself.
Could be a typo.
Okay, thank you very much. And I'm gonna mute myself.
And then I'm gonna screw up pronunciation of your name, Yanis. The positivity violation, did we answer that, or do you still have the question? Okay, okay, perfect. Okay, and I appreciate you stopping me, and please continue to stop me.
Yeah,
Oh,
if we were in person, we'd be stopping you a lot more. So I'm trying to recreate the in-person experience. So
I appreciate
hopefully
it.
that's okay. Sure.
Okay, so let's see. Oh, what I was going to say about positivity just in that simulation case, which is not that important, but again, we would expect the performance to get worse when we introduce these violations, which is what we're doing down here. That is what happens, but it doesn't get, you know, hugely terrible. Okay, so now we want to apply it to MTO, to the, of course, the data that motivated this in the first place. And so just for this initial example, we're just going to use 2 sites, LA and Boston, and we're going to use adolescent school dropout at follow-up. So we're going to use the full data from Boston, and so we're going to completely ignore the outcome data for LA. Using the outcome model for Boston, we want to predict what we think the intervention effect would be in LA, accounting for differences in population composition. So again, as we talked about, that's S going into W, and differences in intervention take-up between the 2 cities. So that's S going into Z. Okay, so here is the observed intervention effect in Boston. So just to orient you, you can see the names on the x-axis. And then here's the intervention effect. This is just risk difference on the y-axis. And so you can see that in this case, this would be, in contrast to our marijuana example in Boston, this is actually an example of a protective effect. So kids were randomized to receive this voucher, and then they had a lower risk of dropping out of school later. And so now we want to say, okay, would we expect this same protective effect to hold in New York, or sorry, in LA? And so we would use our transport estimator. Oops. And this is what we would estimate. We would say, no, we would not expect it to hold. We would expect just a null effect. But we actually do have the data for LA, so we can use this prediction just to get an idea of the extent to which accounting for these factors could explain the difference. And so we can compare this transported effect to the observed effect, and we see that they are pretty close in this case. So again, this maybe would suggest that at least in this particular case, you know, using the differences between the individual level variables at baseline, differences in take-up. We're not using any outcome data for LA, but we were able to get pretty close to the observed estimate. So we did a more comprehensive version of this analysis for a chunk of risk behavior and mental health outcomes in an applied paper. And so I'm showing that here. So this is kind of the same setup as before. You have risk differences on the y-axis, the sites on the x-axis, and then the observed estimates are the solid lines, and then the transported estimates are the dashed lines. So in this case, again, you can see, even though we're not using any of the outcome data for LA in these 2 cases, we are able to get more in the ballpark, you know, not super close, but more in the ballpark. But we did this also for, this was just using the interim data because that's all that had been released at that point. But when we did this for the actual DSM disorders, we found that they weren't transportable. Like our transported effects did not get any closer to the observed effects. In the case of the 2 that we had, so major depressive disorder and generalized anxiety disorder, actually that was an interesting case. So for each of these, I would test that pretty restrictive assumption that there was a common outcome model between the sites, and that actually wasn't met in the case of generalized anxiety disorder. And so then one could then ask whether this exercise was still useful in the case of these outcomes. And I think it was. I think now, like what it did, at least for me anyway, was provide quantitative evidence to then make a decision. Okay, one may want to use a site-specific approach to estimating intervention effects in this case. And so again, why I think that might be valuable is because what has been done in the case of MTO anyway is, you know, folks decide how you're going to use site, but it's really based on opinion. And so at least in this case, you could then go through this exercise and then say, okay, actually, we do want to use site-specific effects, for example. And so it's taking, I think, more of the guesswork out. But as we talked about in the beginning, there are some other reasons why intervention effects could differ across sites. And so I was thinking they could also differ because if there are important mediating variables along that pathway that could also differ by site, that would then result in the overall effects being different as well. And so the setup here is pretty similar to before. So everything is the same in this, well, at least if you look at the model on the right, that's specific to MTO, except for now I'm including an M for mediator between Z and Y. And then the more observed, everything that I've talked about and that I will talk about applies also to the more general structure where you could have an arrow from S to A, you could have an arrow from A to M, A to Y. It's all applicable under that structure too. So it works under more than just this instrumental variable setup. Okay, so in this case, we're interested in the transported direct and indirect effect. And I'll go back. This is the effects that we typically estimate with mediation. So the direct effect here, so I'm going to be talking about the direct effect of A on Y. So in this case, that would be the paths that operate not through M. So you could have A, Z to Y. If I had like a little highlighter in person, I'd be highlighting it. So you would have A, Z, Y, or if you didn't have an instrumental variable, you could also have, and there was a direct effect from A to Y, it would also include that. And then the indirect effect would be the pathways operating through M, so A, Z, M, Y in this case. Okay, and then of course, this is all, because we're talking about transporting, this is all then transported to that new target population. And so here, just a little bit of notation. I'm going to be talking about what are sometimes called stochastic or randomized interventional direct and indirect effects. I think maybe the most common direct and indirect effects that people estimate are natural direct and indirect effects. They actually aren't identified in this setup that we have here where we have Z. In this case, Z is what can be called a post-treatment confounder of the mediator outcome. You can see it's post-treatment, and then you can see it like it has an arrow pointing into M, an arrow pointing into Y. So that is the reason that we're using these stochastic or randomized interventional effects instead. And so in this case, when we're estimating these kinds of mediation effects, we're going to draw M from its distribution conditional on A, so our treatment, and W, our baseline covariates. And that is denoted with this G sub A. So just saying that we're going to have a distribution of M under one value of A, like randomized to receive the voucher, a distribution of M under another value of A, not receiving the voucher, and those are what's going to be contrasted. And so the indirect effects are a contrast of the parameter that I'm showing up here at the top, and just under different values that we set for A prime and A star. So in this case, we have, were you randomized 1, were you randomized no? So, so 1 and 0 would be just substituted in various ways for A prime and A star. And then this is a little detail, but sometimes you might see these effects also conditional on Z. We actually can't do that in this case because then we wouldn't get an indirect effect if we controlled for Z, so we wouldn't be learning anything about the pathway. But that is a very small detail. So again, this direct effect, we're contrasting Y we're holding our draw from our distribution of M constant, and then we're contrasting it under did you receive the voucher, did you not, in the new target population. For the transported stochastic indirect effect, we're now holding A constant under yes, I got the intervention, and then we're contrasting our values of Y under two different draws. So draw from the mediator distribution of yes, I got the voucher, draw from the mediator distribution, no, I didn't get the voucher. This is a bit of a mess. You can ignore it, you can say, but this is just showing these parameters are identified. The notation for this is very much a mess, which is why we have all these different new letters here, but it's not, the identification is actually pretty similar to before. We of course just now have M in the mix instead of just our Y model and our Z model. The assumptions are pretty much the same too. The only thing that is different, instead of having our one randomization, exchangeability assumption, we now have sequential randomization for Y being independent of A, the potential outcome of Y being independent of A, and then the potential mediator value independent of A, and then potential outcome also independent of M, conditional on the past. The rest is the same. So here I'm just showing, we're ignoring the instrumental variable. We're just looking at, okay, what is the direct and indirect effect of A, of getting that randomization on the outcome. And so again, just if we do have data on Y, we can also test this, this strong transport assumption using this non-parametric test for, do we have evidence that these distributions are different? So again, we developed estimators for these effects, still based on this efficient influence function. So very similar to before. So one is an estimator that solves the efficient influence function in one step. It just, sets it equal to 0, solves for it. Sometimes that's called an estimating equation estimator, or a one-step estimator. And then the other one is this TMLE idea that I talked about before that also solves the efficient influence function, but it does so by doing these like iterative debiasing updates, which in this case is in the total effect case, it's not very much of a mess, but in this case, it's a little bit of a mess. But I have code that should hopefully easily do this for anyone who has this as a research question, which you can find at this link. And these estimators, it's actually current work, so we posted it on arXiv, but it's not out yet. But it improves upon an earlier version where I made a couple simplifying assumptions that made this a lot easier to solve. In that if you assume a single binary mediator, it actually becomes a more straightforward setup, a more straightforward estimation approach. So the one that I'm linking to here, this R code, and then the arXiv paper that is current work, it relaxes that assumption. So you can have any number of mediators, they can be distributed however, they can be conditionally dependent. So anyway, just relaxing the assumptions that we made previously. And then here, again, just a few selected simulation results. Just again, showing the robustness, the letters, again, are a mess, and I apologize. There are a lot of nuisance parameters that we're actually estimating here. So that's the reason, but it's just to say we actually have to get our model of Z, which is using the voucher, we have to get that right. That's Q here. It's not robust to misspecifying that. But it is robust to misspecifying a whole bunch of other stuff, which I'm showing as the CGERU, which is just 5 other nuisance parameters. We can misspecify those and still get a consistent estimator. One thing that I wanted to point out is something that I hadn't appreciated, I think, until, I don't know, definitely later than I should have appreciated it, which is that even if we're in this case where we have robustness, we might our coverage might be wrong. Like, we may still be in robustness land, but we shouldn't expect to get 95%. We shouldn't expect our 95% confidence interval to cover 95% of the time, which yeah, I sadly did not appreciate at the beginning of all this. And so you can see an example of that. Let me highlight it. Well, really here. So I don't know if you can see what I highlighted, but in this last row under transported stochastic direct effect, we should have a consistent estimator. We're within our robustness, but you can see that the coverage is 90% instead of 95%. That is to be expected. If we are using parametric models, we could use the bootstrap and we could get close to 95% confidence interval coverage again. But here we're using machine learning, and in that case, we would need a different strategy where we actually target the nuisance parameters directly, which I have not done myself, but other people have. So that would be what one would need to do. In this case, just as with the transported total effects, we applied this to the moving to opportunity study. And so here I'm showing just the indirect effects. So this is the indirect effect of the effect of getting the voucher on behavioral problems scores, the behavioral problem index in adolescent girls 10 to 15 years after randomization, mediated through features of the school environment. And so I used a whole bunch of different measures, so including multiple measures of school rank, number of schools, number of moves, proportion of students receiving free and reduced lunch, Title I schools, whether changed school districts, et cetera, duration weighted over this intervening time period of 10 to 15 years. And so again, these are the path-specific effects then. And so, and I should also say this OS stands for one step and the TMLE stands for TMLE. So these are just the two different estimators that we developed. We would expect them to perform, similarly, hopefully, and luckily they do perform pretty similarly. And then again, on the y-axis is a risk difference, and then our sites are again on the x-axis, transported as dotted lines and observed as solid lines. So we see that looking at the observed estimates, this indirect pathway that we're looking at is protective for girls in LA and New York City, so resulting in a reduction of behavioral problems at this final time point. However, the same pathway appears like it might be harmful for girls in Chicago, which is actually kind of common when I looked at this across multiple. This is just an example of one outcome, but when I looked at multiple similar outcomes, you kind of saw this pattern where the effects were either protective or null in other cities, but in Chicago, things were not, things did not look as good. Anyway, by taking so what we did here is we compared the estimates, the observed to the transported again for Chicago, and we see in both cases, the two are like pretty similar, understanding that there's some wider confidence intervals. So that means that by taking the outcome model for LA and New York City, standardizing based on our baseline covariates W, using the voucher Z, and our mediator distributions, M, joint distributions, we can get a predicted effect for Chicago that is more in the direction of the observed effect. So it looks like we are able to explain a lot of this initial disparity in effects between sites. In contrast, if they weren't close to each other, I think this would suggest that the identification assumptions weren't met. And in the case of MTO, my guess would be that it would probably be this common outcome model assumption. I think that one is probably the most tenuous, but of course, if we have unobserved important confounding variables too, of course. And so that is really what I had today. And so I wanted to, of course, leave some time for questions and thank the folks who I was able to work with on this who are listed here, and the funding for this work. And I see that posted the link. Thank you for posting the link to the code to do it.
All right, thank you so much, Kara. And if there are questions, please feel free, anybody, to jump in. And I'd also just like to particularly encourage any students on the call. If you feel like you have a question, then just speak up.
Yeah, people should know that they can just unmute themselves and ask a question. Or if you're feeling shy about doing that, or your setup isn't great at home or whatever, feel free to type it in the chat, and we'll see that as well. Maybe I'll just ask while we're waiting or people are formulating their thoughts. And I apologize if you showed this and I missed it, but I'm impressed what a good job you're able to do in getting these. I mean, I understand that it works better for certain measures than others, but what was in your W?
So many things. Yeah. Oh my gosh, so many. Yeah. So it's a whole bunch of variables about the individual, the child themselves, as well as a whole bunch of variables on their parent, that is the primary parent enrolled in MTO, and their reasons for choosing MTO, their background history, all of that. Variables about like their baseline poverty level. If there were other, I'm trying to think if there were other really like administrative variables like that about the neighborhood. But yeah, it's really like, have they ever used Section 8 before? Do they have other forms of government assistance? I mean, there's tons. I think that there were, over 20 for sure. And if you look at the distributions of those variables, they are pretty different across the sites. Like even just using a very like just thinking about only race ethnicity, that was vastly different across the sites.
Right.
Mm-hmm.
Yeah, that's helpful. I've tried to do similar things just with intention to treat and multi-site randomized experiments, and had, varying success. So actually joint work with Liz. Yeah. So, and so sometimes it worked well and sometimes it didn't. And it really all depends on whether or not you can satisfy the assumptions. And so for us, it clearly wasn't just about the demographics that we had access to. There were all these other variables that we would have needed and didn't have. So yeah, it's hard to parse how much is the method and how much is the data, right?
Yeah, I mean, I compared it for the total effects for that project. I also, this is also on my GitHub, but I have like the more standard estimators of IPTW and G computation. So focusing on the, everything that you would put at all those probabilities that you would put in the denominators, so that weighted estimator, and then if you just focused on the outcome model, stepping back, I have those also. And so I did compare with those. IPTW, as you might expect, was not super helpful because the confidence intervals were just so big, because you are, for each of these, I think because of the Z, you are multiplying by, you have to multiply probabilities together. And then, anyway, it was very unwieldy. But yeah, like G computation and TMLE, from my recollection, they did perform pretty similarly in that case. But we also have, like I said, just so many variables. I tried to do this for another project in which there were very few, and it did not work at all.
So could I ask a kind of a meta question? My name is Pat Shroud. I really enjoyed your talk. It seems like, well, I'll have to look at your papers to understand it deeply, but it seems like there's a framework here that's possibly relevant to a very interesting talk in the same series last year by Liz Stewart from Hopkins, who was talking about how something can be called evidence-based in education, and it's based on one study. And I'm just wondering if your framework would help characterize findings that are likely to be robust and are likely to transport versus findings that aren't. You know, so if we give hungry kids food, that's probably going to transport better than if we try to affect some more complicated social structure. But in schools, it seems like maybe there are going to be some things that are going to be a little bit simpler. And I'm just wondering if your framework can provide some value at trying to talk about how a single study can be considered to be evidence-based for policy.
Yeah, I think that is such oh yeah, I mean that would be so valuable for sure. And that was one of my other interests in pursuing this and writing. I wrote, like, this is funded by this Kangaroo mechanism through NIH. And one of the reasons why I wanted to write it is because of that, like, larger question. I was really interested in the nurse family partnerships from a long time ago and how that was then expanded under the ACA. And then they had very different results across the sites where they expanded it. So yes, I was, and so I do think that, you know, you could use this maybe to say, well, this is kind of like working, this is transporting, even though these marginal effects that we see look different. Once we, you know, do this extra exercise of, but what should we have expected them to be different given the participant distribution, and then, you know, any other intermediate variables that we have access to, then I think it could say, actually, you know, on the face of it, it looks like this intervention isn't working the way it's supposed to. Whereas if we do this, if we apply this framework, go through this exercise, it could say, no, like, this is actually working how we expect it to work. Mm-hmm. Yes.
Okay. If nobody, I already asked the questions. If nobody else wants a first question, I'll take a second. Okay. So one is a comment, it's really not a question. So I come from political science, and we have a lot of people interested in sort of economic development, you know, experimentally. And there's a lot of, no, I shouldn't say a lot, but a bunch of work sort of combining these. And you come out of biostatistics. Jennifer mentioned education. And I'm wondering if we can unsilo ourselves somehow, you know, to put together your biostatistics, to put together a more medical thing where, again, you get these, as Pat said, you know, we do one experiment on a statin and we find it works, and then somebody else finds it doesn't work, and the tox report doesn't work, and then the third one works. But particularly in development, you know, the question is, where do they transport? What are the characteristics? Is it a function? And then even the treatments are differing. So it's a function of, you know, for UBI, you know, what you need to get people in Kenya is very different than what you would need in the US. So I'm wondering, so that's just a suggestion that we sort of put together these various literatures. And I have learned a lot from your biostatistics citations, which you didn't know. And if you don't know the political economy ones, you can send me an email and I'm happy to pass them on. And it'd be nice if we all sort of work, you know, work together. Okay, so that's my, it's not a question, it's following on with Pat's suggestion that we move away from single experiments and thinking they're evidence. But the question I actually have for you is, on MTO, there's actually two treatments. One is just getting a Section 8 voucher, and one is getting a Section 8 voucher, which what they really cared about, where you had to move into a somewhat better district. And I'm wondering if you sort of couldn't leverage that. So one of the differences, like from the Chicago was it Gautreaux, which was an experiment, people who went far away from Gautreaux did really well. People who moved next door to it didn't do very well. Of course, it wasn't. People do different things. So I'm wondering if, you know, you could sort of leverage the geography or something. Just, you know, so maybe in LA, it's harder to leave, you know, sort of the project, whatever, high rise, to go to a better area, whereas in another city, it's easier to leave or something like that. Or maybe more people just left or something like that. or to leverage Raj Chetty's stuff, where again, there's no effect if you move on kids if you move after they're 10 or 12 or whatever. But a good, you have a little bit of that, but to sort of more formally leverage those kinds of things.
Mm-hmm.
And I guess that would be in a second study. So you take advantage of, you learn something, and then you'd have to convince Trump HUD to do another MTO or something. But I mean, Pat said it's multi-site stuff, and you yourself said, I think external validity, which is what I call it, is sort of the key issue. What can policymakers, learn? Seems so far everything we've learned about I'm going to stop in a second. Everything we learned about education, comes from 2 studies that were done in the where everything about education and how well people do. 2 studies from the 1970s. It seems we ought to have more than.
Yeah, I think that those are really good points. And your first one about that there were actually 2 of the Section 8 arms, which I didn't talk about, that is a really good one. We explored it. I tried, I did sensitivity analyses and show that it didn't really matter whether I was using, just you get the voucher alone or you get the voucher plus the help, and the requirement, though it didn't happen in practice, to move below a certain level of poverty. So the results were pretty much the same for the analyses I did, regardless of that. But then I did also want to explore, well, what about the people that did, like you said, what about the ones that did move to much lower poverty neighborhoods? We didn't find like marked differences with that either. And then for this mediation work that I showed at the end, I did include the duration weighted value of their neighborhood poverty over the 10 to 15 year period. So we are allowing that to be different by site, at least for the direct and the indirect effect estimation. Yeah, because like you said, like that is something that could very plausibly differ between the sites. Mm-hmm.
All right, so
great stuff. Great talk. I just, not a question, comment. Great.
Thanks everybody. So in the interest of time, let's cut it off here. I think everybody can find Kara online and follow up if you have more questions. So thanks everybody for participating. Let's thank Kara again as best we can virtually for her great talk.
Thanks so much for having me.